Now that we have seen the basics of electrodynamics and we have seen what the four potential, the electromagnetic field tensor and the four current are, we can move on and derive the equation of motions for the charged particles. Therefore, we are going to see how magnetic fields affect the trajectories of charged particles. So let's see. Particles in a fixed potential. Fixed, this word is very important. Now I'll come to that. So now what I'm going to do is to neglect the interaction between particles and particles if there are more than one. So if neglect interaction between particles. So if I have more particles embedded in an electromagnetic field, then each of these particles is going to feel the effect only of the potential in which they are embedded, not the interaction, not of the potential which is related to the other particles. Okay, so they only feel the field, but not the other particles. Then what I'm going to do is to study the interaction between the field and the particle. So I am going to look how the field is going to affect the dynamics of the particle, but I'm going to neglect the effect of the particle on the field. Because again, think, if you have a magnetic field and you are plugging in a particle, this particle has its own electromagnetic field, right? Therefore, if we plug it somewhere, its contribution is going to add to the one of the fields, of the surrounding fields, right? So I'm going to neglect that. So the assumption here is that whenever we have a particle, it's going only to feel the fixed potential that is surrounding. Okay, that's why it's fixed, it's there, it's not changing, and is not affected by the presence of the particle itself. Now we want to go for the equation of motion. Therefore, the first ingredients that we need to derive is the action of the particle. We have done this for the free particle, right? We have seen that S was equal to SP for the free particle, and now we are going to include the interaction between the field and the particle. Okay, I remind you that SP, so the free particle, was minus mc squared, and then we have the integral over the tau between position A and position B. Okay, and the integral is along the word line, so in the four-dimensional space. Good. Let's give a look now at this SPF, so the interaction particle field. So, well, what is the only property associated to a of a charged particle? The charge, Q. So we are going to have Q as the only parameter associated to the particle. Then, for convenience and to set the unit of measures, one divides it by C. There is divided by C because then it cancels in other equations, so it's convenient to have it there. And then it sets also the unit of measures for the charges. Integral between A and B, then we need the potential, and we keep the simplest bit of the electromagnetic field potential that we have, which is the 4 potential, not the full electromagnetic tensor, but we only take the 4 potential, out of which the electromagnetic field tensor is derived through derivatives. Remember, is an antisymmetric tensor based on the derivatives of this guy. But here is sufficient to use the 4 potential, and this form of the Lagrangian comes mostly out of empirical consideration that you kind of understand now, because this is just for convenience and to set the units for the charges. This is the only property of the particle, so Q is the property of particle for the charge that is relevant for the interaction between the electromagnetic field. And what we want for this action is to be a real number, which it is, because you see we have a scalar product here, because you have the symmetry, mu indices repeated up and down. This is the scalar product, which is a real number. That's good. Q is a constant, because a particle has that value of charge, and this is constant, like could be C, and therefore if you wish, so Q is constant, and if you want, this is invariant, in the sense that if we apply a Lorentz transformation to the whole object here, Q is not going to change, but A mu belongs to the Minkowski space, and therefore is not invariant. Okay, therefore this guy here, we should be an invariant scalar. It's actually not invariant because it contains this guy, but it doesn't matter, because here what we are looking for is for the action of the particle, and that's the only properties. What we are looking here is the action for a particle embedded in a fixed potential, So here, whatever it is, it's assumed to be fixed, given. Okay, so remember, this is not playing into the equation of motion. It's just the actor of the equation of motion, in the sense that there is a guy fixed, and the particle is going to behave accordingly. Okay, so this is not invariant, but it doesn't matter for this reason. Then we can, if we want, we can reshuffle this equation a little bit to relate the Lagrange, the action to the current, to the force current of particles. So what I just do, I just keep 1 over C here, I let it outside. This is C. Integral between A and B, I bring Q inside, A mu remains, the X mu remains, and then I divide by dt, and I multiply times the dt. Okay, good. So what is this guy here? This is actually, and multiplied by Q, this is related to the current, to the force current, because I have A mu J mu dt is my new action, where we have, you see, where we basically have defined J mu, as we already said, as Q times dx0. Well, let's do it explicitly. So we have Q dx mu over dt. Okay, let's see what this guy is. So we have Q times dx0, which is ct, c dt divided dt. This one disappears. Then we have Q times dx1 over dt plus then dx2 over dt, and so on, which is nothing but the velocity. Okay, therefore this guy, so I transposed, so this guy is equal to QC, and then we have the standard current, and this is our J mu, which is defined this way. Okay, that's why it was not it was not derived as Q for velocity, but Q and then the x mu over the t, not over the tau. Okay, good. Now that we have the action, we can go for the Lagrangian. Which is hidden into the action, right? So now what we do is to use the total Lagrangian, and therefore we are using the total action. Now we know the two of them. Therefore we have S, the integral AB of minus mc squared d tau, that's related to the free particle, plus Q over C A mu dx mu, and this is related to the charged particle. That's this guy here. And then I introduced also this derivation related to j because it's also convenient. It will come up in a following derivation. Okay, so just keep in mind that you can use for the charged particle you can use these two actions. And I just wrote it in here. Now what we have, I can kind of explode the term the x mu, sorry, a mu, which is equal to phi a. Look, I didn't write transpose because the index is below, therefore this is the dual vector. Okay, if you want, is the one form related to a mu vector with the index up, and I just write it in here, integral a b, then I copy mc squared d tau. Then we have the scalar product. Remember that there is the metric hidden inside. The first term of the metric is -1. Therefore, we have minus q over c phi, and then c, and then the x0. The x0. Okay. Then what we have? Plus q over c, and then we have the rest of the vector multiplied by the x. AE, the XE. Okay, so I exploded the symmetry. I split the time component from the space component. Now what we do, I just express the tau as gamma t dt. That's the proper tau. That's the proper time. How is it related to the time? Then I define the xi equal to the ri. So just for convenience to remind you that is only the space component, just to be sure that you don't mismatch that. Then we have the x0, which is equal to c dt. And then what we do? We plug it here, we plug it here, and we plug it here. What we get is the integral between a and b of minus mc squared gamma minus 1. Now I'm extracting delta t. You see, I will put gamma delta t, gamma minus 1 delta t, and then I extract outside the parentheses. Okay, so let's take it in a whole. Then we have minus q phi, because we have this is c dt, the c drops, and the t also, this one I want to put it outside the parentheses, qc ai dxi dt dt. Okay, so now you see that this delta t was here, and then I just divided and multiplied by delta t to have it like that. So you see that this guy here is vi, the x over the t, you see. And then we have and here we have the current. If we vi multiplied by q is q vi is equal to the three-dimensional current. Okay, good. This is the Lagrangian. So this part here is the part of the Lagrangian that basically refers to the interaction field particle only in this direction, and this one guy here is the total Lagrangian for one charged particle. Good. Let's now let's get a clean piece of paper. Good. So now that we have the Lagrangian, we can continue and find the generalized momentum. So we are moving toward the Euler-Lagrange equation. Now that we have the Lagrangian, we can define the generalized momentum. Let's write it here. You see, yes. Which is simply the derivative of the Lagrangian with respect to the velocity, which is equal to, now we are taking the derivative of the first term. Remember that in gamma there is hidden the velocity, and we have our standard m gamma v bar that we already derived and that we know to be the momentum of the particle. Then we have the derivative with respect of the velocity of this term, but phi depends only on the space components. This is only a constant, and therefore this is 0. Then we have plus q over c ai, because this doesn't depend on the velocity, and the velocity, derivative of the velocity with respect to the velocity is 1. That's what we have. So this guy here is equal to the generalized momentum that I distinguish from the standard momentum with these pedix here, okay? And this guy is belong to R3, so you see I'm now doing a three-dimensional approach, okay? I derive the Lagrangian, and then I'm using the Euler-Lagrange equation in this form, only using as a only using the velocity and the space as independent component, not in a full covariant way, okay? Good. Now that we have the generalized momentum, we can derive use the Euler-Lagrange equation to get the equation of motion. Use Euler-Lagrange equation to find out the equation of motion. So they are derivative of the generalized momentum over the t. You can recognize that because that's d over dt of the L over the V, right? So maybe it sounds more sound to you. Okay, then the L over the R. So you can recognize the Euler-Lagrange equation, right? This one I already computed, that we have it. That's here. So we just plug it in, and we need to find the derivatives for the time. So I just call this one and this one 2. So let's work on the first bit. So we have the p bar over the t that we want to plug it in, and that's equal to t over the t, and then it's equal to this is the momentum p. This has the pedix, this doesn't have a pedix, is the standard momentum for the free particle. Okay, plus QCA. Fantastic. Then we have the other part, 2, which is the derivative of L over the R bar, but it's nicer to see it as the gradient of L, of the Lagrangian, which is equal to, now we just plug in the full Lagrangian as we have it here, okay? And we have this component is disappears because it doesn't depend on the position. You see, derivative with respect to the position here is a constant, and this one depends on the velocity. There is no position, this drops. But we have this guy here, so we have minus q, and now we have the gradient of the variable phi that, yes, it depends on the position. Then we have plus q divided c. Then we have this one depends on the position, therefore we have the gradient of A times the velocity, times the velocity. Okay, perfect. Good. Now what we do is to reshuffle a little bit these equations so that there are terms that cancel. And for example, we can take this term here, the v, which you see is a vector. So it's the gradient of a vector, and this can be re-expressed in another form. So you can, this is equal to a gradient v plus v gradient a plus v rot a, where with this guy, with so let's say vector a, vector b is equal to a b. Okay, I do like this, otherwise I get too messy. Like this, which by the way is also used, this sort of notation. A rot v. Okay, but we have that this guy is equal to 0. The rot of v is equal to 0. Then we have, where is it? This guy here is equal to 0. Again, because v is equal to constant. This is left, but then we can notice that this guy here, we can get rid of it, because whenever we have the derivative of d of the dt applied to a, so I now work only on this term, dA over dt, this is equal to that's the total derivative, therefore the partial derivative with respect to the time, plus the partial derivative with respect to space r dot I times the velocity. Okay, just the definition of the total derivative with respect to the partial derivatives. And this guy here, I just rewrite it so that you see it clearly, dt plus v, r dot is v vector gradient of a. Gradient of a. So we have v gradient of a here, which is in the equation on this side. We have v gradient of a, which is on the equation on this side, and therefore they cancel. What we are left with is with this guy here. So we have the p over the t, the p over the t, and is this derivative here. Okay, so there is not the pedix here, because this guy here is this one. Okay, so the p over the t plus this guy that I exploded in this way, but we have seen that this part is equal to is going to cancel away, so I only keep this one. So we have plus q over c dA over dt equal, and now comes the other side where we have minus q gradient of phi that we didn't touch, plus this part here that survived. Therefore we have q over c, this one is equal to 0, this is equal to 0, this one and this one dropped away, we are left with that v rot a bar. Nice. So now we know that this is equal to the force, so we have the force that the electromagnetic field is exerting on the charged particle, which is equal to the p over the t, so the force is the change in the momentum that we have. So I basically write this one equal to the rest. So I bring this guy on the other side, q over c dA bar over dt, then minus q gradient of phi plus q over c v rot of a. And now look, this is related to the electric part of the component of the field, and this is related, the rotor is related to the magnetic part. And out of this I just define as E as the guy which is minus 1 over c dA vector over dt minus gradient phi, and I say that, and I call B as rot of A. Here I get the relationship between the third-dimensional potential of the vector and and E and B. And my force is going to be Q, you see Q, Q, and then the rest is this vector E that I created, plus Q over C, and then we have the rotor. Now I just write it as V cross B. Remember that this square thing is the X here, and this is the Lorentz force. Okay, print this equation with ink of fire in your brain. Okay, so you basically see that there is the contribution of the electric field, which is pushing the accelerating the particle along the direction of the field, whereas this one is going, the force is going to be orthogonal to the direction of motion of the particle. So this is basically along E as a direction, whereas this one is going to be orthogonal to the velocity. Okay, so if you have the vectors, velocity and vector, the force is going to be orthogonal. Therefore, it's going to bend the trajectory of the particle, whereas this one is going to give a linear acceleration of the particle. So this is about the force. Then what we can also derive is the work. That's a very easy derivation as well. So now that we have the force, we can derive the work, because the work, sorry, let's do it this, is equal to the change in the kinetic energy with respect to time. So because we are giving or removing energy through work, so the kinetic energy is going to change, which is equal to V dP dt. Okay, look, take care that this is the actual momentum, so it's mv, so it's mv square. That's the kinetic energy. Yep. Equal to, now we just plug our momentum in here there, because we just have it. Okay, so we just plug all of this here, and now what do we have? We have that this is going just to be equal to QEV. Why is that? Well, because we just have the scalar product between E and V, and that's fine. But then if we also multiply V per Q over C, V cross B, we basically have the vector V cross B, which is orthogonal to V. Therefore, this guy here is identical to 0. This is identically 0, because V is orthogonal to V cross B. V cross B, the velocity is orthogonal to the vector, and it is going to be identically equal to 0. Therefore, only the electric field does work. Only E does work. It produces, is the only one that produces work. And only if you have that EV is different than 0, of course. Okay, because if you imagine that the electric field is oriented in this way, one direction or the other, doesn't matter, and the velocity of the particle is orthogonal, then the scalar product is equal to 0, there is no work done. Okay, and that's it.